Um, so far, there have been a lot of solutions presented, which is really great. Today, I'm going to talk about column. So I'm going to spend a lot of time on describing the problems that I see in DPDK. I probably don't have a great solution, but I have tried to put together a solution. So we'll see what everyone thinks. All right. So the agenda is going to be a lot of background information, which try and explains the problem that I see. I'll corroborate that with some performance data that's available in open source. Then I'll introduce a little bit about what are custom PMDs or custom metadata in the PMDs. There have been efforts done, some efforts done in the form of dynamic MBUF from Thomas. We'll see how this one differs from that. I'll also talk a little bit about some of the advantages and disadvantages. Right. So jumping into the background, how are the applications integrating DPDK? All right. So to look at this, I have categorized the applications into two broad categories. The applications that were written pre-DPDK, prehistoric, and then the apps in the post-DPDK world, right? And then when it comes to integrating applications, there are several parts to it. One is the control management plane, which involves configuring the device, querying the link status, querying the statistics, etc. And today that forms around 95% of the driver code. And that's not very important from performance perspective. And then you have this data plane integration where you receive the packets from the NIC and you do packet processing, right? And today that forms probably 5% of the driver code, but that matters 99% of the time in terms of performance. Okay, so so what happened in the pre-DPDK world, right? So in the pre-DPDK world, there were a bunch of SDKs. Every vendor has his own software SDKs, and they came up with their own control plane and management APIs. And they also had their own descriptor layout and metadata layout. Some of them had a metadata, or most of them just exposed the descriptor to the application. Right? So now you have this application. Due to business reasons, the application vendors had to integrate two or more of these SDKs. So in order to do that, they introduced the hardware abstraction layer. This hardware abstraction layer kind of made sure that the application is independent of the underlying SDK. So it kind of made sure that it provided a single view of all the SDKs to the application. Okay, so from that perspective, you can take that application and just modify the hardware abstraction layer, and you can run it on another hardware platform, right? So along with this, the application also had some of its metadata, which it carried from different layers within the stack. Okay, so how does that hardware abstraction layer look like? So here, I'm using some of my past experience. This is what I saw, which might be a little bit different in different applications. So the hardware abstraction layer, in my perspective, was implemented in two broad categories. One, using abstract APIs, and the other one, used common metadata. Okay, so so how does the hardware abstraction layer implemented using abstract APIs look like, right? So here, there were APIs created to get and set different fields from the descriptor. So this was the approach followed in ODP, which is another project to provide similar capabilities like DPDK. So the hardware abstraction layer would implement those APIs, and the application is written to those APIs. So some of the disadvantages that I find with this approach is if these functions are implemented as non-inline functions, it's a performance hit. So it happened in ODP. Earlier they were implemented as inline functions, but at some point they decided to move to non-inline functions, and in a typical application like L3 forward, there was a 20% drop. That's because you want to access so many fields from the descriptor within your packet processing path that function call becomes an overhead. Right? So what happens if they are implemented as inline functions? Now you get the performance, but your application is not binary portable. So you have a SoC which is based on same CPU architecture, but your hardware accelerators are different. They have different descriptors, different descriptor formats. Because you implemented those as inline functions, now you cannot take that binary and go run it on another ARM-based SoC. Right? So the other issue that I find is you cannot use vector instructions anymore, because there is no fixed format of the descriptor that the application is aware of. So it cannot use vector instructions to access those fields. I also kind of think that it's not, it doesn't work so well on server platforms where you don't know what kind of NIC you are going to have in your system. So I feel there's a more dynamic approach required in this case. Right? So to address some of these issues, some of the applications came up with this common metadata. So this common metadata is the metadata that the application wants from your device, from the NIC device, right? So this is very similar to the concept of RTE-MBUF in DPDK. So do note that along with the common metadata, you still have the application metadata. So now between the SDKs and the hardware abstraction layer, you have got these conversion functions. These conversion functions are specific to the SDK. So at the lower interface, they understand the descriptor, and at the top interface, they understand the common metadata, and they do that conversion. Okay. So now, the application is written for that common metadata. So now the application understands the layout of the metadata in memory, and it can use vector instructions efficiently. But some of the disadvantages here are, the moment you have this common metadata, you are starting to touch additional cache lines, which means you are going to hit performance issues. You are going to drop the performance. Okay, but yeah, you could go ahead and use the vector instructions now because of the known format. Okay, so I think those were the couple of methods in which that hardware abstraction layer was written. I don't know, there are a lot of application vendors here, I believe. I don't know if your methods fall in any of these two categories. So feel free to talk if it is different from these. Right? So now, coming to the applications themselves. The post-DPDK era, what happened to the applications that were written post-DPDK? Right? They have fully embraced DPDK. We love this. We love these applications. They are like DPDK through and through. So they make use of the MBUF fields, And they still have, in my opinion, in my experience, I think they still have to have that application metadata, which is not part of RTE MBUF, but it is specific to them, and they have to carry it around. And it might be very light, but they still have to carry it around. All right? So what that means is, again, that application metadata is in an additional cache line because they cannot touch RTE MBUF. So some questions that you guys have to ask is, how many fields from RTE MBUF are getting used in your application? Are you using all the fields from RTE MBUF? Right? Is there scope for optimizing the overall number of cache lines touched? So if I consider the RTE MBUF and the application metadata as one set of metadata, is there scope for optimizing based on how many fields you don't want out of RTE MBUF, right? The lesser number of cache lines that you touch, the more performance it is, right? And I think, I feel if there is, if the metadata in total is packed closely, you can have better vector instructions. You can make use of vector instructions much better, is my opinion. Okay, so I think we are fine here. So now, going back to those pre-DPDK applications, they have integrated DPDK, but how have they done it, right? I think there are two scenarios here. In the first scenario, they have treated DPDK as another SDK. So they still have maintained their common metadata, and they still have their application metadata, and they might have several reasons. Their whole stack was written for this common metadata that they created, and they are not in a position to go change all their stack code. Or that stack might have exposed that common metadata as a interface to other applications, so which becomes an ABI at that point. So they have kind of treated DPDK as another SDK. So what that means is they have written a conversion function on top of DPDK, which takes the RTE MBUF and converts and creates their common metadata. So this is the worst case scenario wherein we are touching, I think this is the case where we touch the most number of cache lines. Okay? So now scenario 2, it kind of falls in the previous case that we discussed, wherein the pre-DPDK applications, they also have embraced DPDK through and through. So here they might have gotten rid of common metadata. It depends on their use case. They might have gotten rid of that conversion function, right? So we will leave it at that. So now, why am I talking about this, right? So as I said, the more cache lines you touch, it is going to affect the performance, right? So I have taken some of the data that's available in open source. This is the data from VPP, which falls in scenario 1. And by the way, in scenario 1, I feel this scenario gives us the a best way to look at how DPDK stacks up against other SDKs in this particular use case. All right. So going to the VPP performance data. So VPP integrates DPDK, as well as it integrates Intel AVF drivers, which I call as SDK in this case. So here is a test case which runs IPv4 forwarding on a Skylake machine with X710 NIC cards. There is the Ethernet IPv4 scaling with 200K routes. So that today performs at 17.49 Mbps per core. Okay? The same code, when ran with the Intel AVF drivers, it performs at 23.14 Mbps per core. Okay, so there's a difference of 32%. With the native drivers or with the SDK, it performs 32% better. So I ran these tests in my lab. I saw even more better performance. But this data today, you can go ahead. It's available on that link over there, and you can go look at it. And there are various other test cases that are run, and all that data is available. Okay, so this is the problem I'm talking about. How can we reduce the number of cache lines that the application touches while using DPDK? Okay, so now, what are custom PMDs? So this is one solution that I think can help, but there are a lot of issues associated with it, a lot of things, lot of work to be done and all that, but we'll see. So what am I proposing here? So what I'm proposing here is we should allow the application to write its own RX and TX data plane calls. Instead of the application dependent on the Ethernet RX and TX burst APIs, can we allow the application to write its own RX and TX functions? So application gets access to the descriptors directly. It creates the metadata that is just enough for its use, which means that the custom metadata and the application metadata can be compressed into lesser number of cache lines. So it can still make use of the configuration and management interfaces that DPDK provides. That is a major part of the driver code. We can still make use of that, but I'm just saying that the RX and TX functions, which kind of make up 5% of the driver code, could be exposed to the application. Right? So obviously, this requires that the RX, TX queue structures are exposed to the application. I'm sure there is more to it. More things have to be exposed from the drivers to the application. This is just one example I am taking here. So this is another ABI. So that's another application that's another interface that the drivers have to expose to the application. Okay. Yes, so RX and TX queue structures have to be exposed. So now, if the application wants to support multiple NICs, then there needs to be infrastructure and APIs provided for the application to query what kind of a device it is, so that it can match the right RX and TX functions for that NIC. So yes, that's additional APIs. So some of the advantages that I see with this approach is it allows for most optimal usage of cache lines. I think this is the best performance that the application can get. And if the application wants to go do that extra mile, if they want to go write this RX and TX functions themselves, yes, they can do that. It allows for vector instructions to be used in the application. Today, CPU vendors are putting more and more wider SIMD engines, and I think this fits well with that trend. The large part of the driver code gets reused. What I meant by that is the configuration and management and all that code remains the same. We still would use the DPDK interfaces. Obviously, no need of separate SDKs, less code to maintain and support overall in the industry. Everything would be under DPDK, and it would be maintained there. So some of the disadvantages. So now the application is aware of the underlying NIC, and this is totally opposite to what DPDK is today. DPDK is trying to hide all the underlying hardware details from the application by creating this RTE buff. But here, I'm suggesting that we break that model and go build, go expose the descriptors to the application. I see that some of the internal structures which are currently internal to the drivers need to be made public, which adds the burden of maintaining another set of ABIs. What that means is you might not be able to update your drivers as frequently as you do today. Okay, good. So that's all I have from my side. This is just one proposal, but I think probably this is the most extreme. But we have to kind of try and find ways to help the applications reduce the number of cache lines that get used, so that the applications can get the best performance. So any questions?
Yes. Basically, but if the application is, like you said, the most expensive is the RX burst and TX burst. But if the application writes it, it will be obviously less optimized than if the developers of this NIC wrote this RX and TX. It will be never as optimized as the original code. So you're saving cache lines, but you're hurting the performance, basically.
I would say yes and no. I would say it depends on how well that NIC is understood by the application developers. I would think if there's enough documentation, you can go write it. But I do agree, yes, that's the pain, right? I mean, but what I'm suggesting here is if somebody is willing to take that pain and achieve that extra performance, they should be allowed to do it. So.
You was first, you're next. I've got the mic already. I hate to pick on your example of VPP, but I will. If you look inside at the VPP code, they want to keep all the data in their own internal data structure, and then they bang in and out from that internal data structure to an MBUF. So no matter what you do it wouldn't solve the problem for VPP, what you're proposing, because they're going to want to keep their internal data structure. Going in and out of MBUFs, you'd still have to do. You'd still have, because the driver is going to still talk MBUFs. And so the problem of going from internal data format to MBUF is still going to exist, and that's the fundamental 30% difference you see.
Yeah, so in my proposal, what I'm saying here is, so this 30% difference here is exactly what you said, right? Converting from the RTE MBUF to the VPP metadata, right? So it's mostly because of that. But what I'm proposing here is, if we expose the descriptors directly to the application,
it wouldn't help. VPP is going to want to use their internal data formats because they're treating DPDK as an add-on plugin, not as a native solution. And because it's not native, you're still going to have a translation layer in the plugin.
Yes, we will have a translation layer, but that translation layer would go from descriptors directly to the VPP metadata. But we would skip the RTE MBUF conversion there, right?
Okay, so you skip one level in direction, yeah.
Yeah.
But still, the overhead of going from descriptor to internal VPP overhead is going to be...
Yes, yeah.
And you can't vectorize that unless you want to vectorize VPP code.
I mean, now the descriptor layout is known to you, right? If we expose the descriptors to the application, the descriptor layout is known, and your common metadata layout is fixed. So I think you can use the vector instructions there.
Right, but I mean, it's part of the VPP domain, not the DPDK domain at that point, yeah.
Yes, yeah, okay. Yeah, I agree, yes. But, the other comment of why did I take this example, right? So this is what is available today,
Yeah, I understand.
So it would be good for private application vendors to take a look in this context and see what happens in their applications. So I'm taking this as an example, but it applies to all other applications.
I think you did a very good evaluation for this, and I mean, what you want to do is also to adapt to VPP, right? As your concept proof for this automation, or some other applications are there.
Yes, yeah. I mean, so as I said, VPP is just an example I have access to in the open source, right? So I took it as an example, but I believe based on the way the applications would get integrated with DPDK, similar problems exist in other private applications as well, closed source applications as well.
Okay, so did you have any sample code or some POC code already prove that your concept can, for example, you can run it in the VPP side so that you can get the more performance compared with current VP copy many buffers, metadata? Do you have any POC code already?
No, I don't have a POC code. So I wanted to reach there before this presentation, but I could not.
Okay.
So, but I think this graph gives you that feel for how it would look like.
Yeah.
Right? If we had to implement that POC code, what we would see in terms of performance.
Yeah,
right?
actually, we also have such kind of consideration as well. As you said, that AVF is a native driver. It can give us very good performance. And VPP is that you have to copy something from the DPDK and metadata to VPP metadata. So I think we are much alike. So we are also trying to see if you have some code to approve that kind of things, we can maybe leverage each other to do that kind of stuff.
Yes, yeah, I think, I will have that POC code. But through this talk, I think what I'm trying to kind of get a consensus is on the problem definition. So if we want to go ahead and make these changes to DPDK, we first need to agree on the problem. Is there a problem? Right? So unless we agree on the problem, we won't be, because coming up with a solution, I feel, is the easier part. So we can come up with a solution. But the difficult part is agreeing on the problem.
Yeah, okay.
So I think you have all the computer science body behind you to support this. I think it just feels like a very traditional trade-off of abstraction versus performance.
Yes.
Every single bit of code I can ever remember, if it looked ugly, generally performed really good, and vice versa, right? So, but for the specific case, do you think there's fundamental thing that prevents people taking DPDK and just writing their own device drivers? If I can tell, people don't do it because they don't know how to do it. That's why they're using DPDK.
Yes, yeah. So, yeah, like I said, it depends on people's willingness, how far they want to go. And I think 30% in this case, in this situation, is a good enough performance for which people want to put effort. So, yeah. Okay, good.
Thank you very much.
Thank you.